In this video, we're going to be talking about moving averages, but we're going to be talking about them from a theoretical standpoint in the digital signal processing world. I hope that you can come away from this video with a better understanding of what moving averages really are and how you can analyze them to better your trading. So first off, this video is meant to be a companion to this book, Rocket Science for Traders. It's not necessary that you read this book, but one of the reasons that I wanted to make this video is that the author of this book states in the beginning that this book can be read at any level, but it really cannot. And I don't think he does the best job explaining what is going on. So, little preface here. First is I'm an engineer, and I've only got a limited background in digital signal processing. So this video isn't meant to be all-encompassing, and there's some things that I've left out. So in this video, first we'll cover complex numbers and the Fourier Transform, then we'll cover some filtering, and then the digital filters used in trading, typically the simple moving average, weighted moving average, and exponential moving average. So let's start out with complex numbers. You may have remembered from your time in algebra in middle school that I is used to denote an imaginary number, and I is simply the square root of 1, whereas a real number can be any real number, any decimal, any integer, and then a complex number is just the sum of a real and imaginary number, so it has a real part and an imaginary part. So, and complex numbers are pretty easy to understand. Basically, we're all familiar with this, right? So we've got x and y, and then we can have a point that's at x, y, in this case it's at 3, 5. And those coordinates, 3, 5, are what's called Cartesian coordinates. Similarly, complex numbers can be thought of the same way, where we have the real numbers here on the x-axis, and we have imaginary numbers on the y. So in this case, we've got a real part and an imaginary part. Like I said, we've got Cartesian coordinates, x and y, real, imaginary. In this case, it would be written 3, 4i. But we can also think of these in polar coordinates, and this is what we're going to be doing in this video. So we have r, which is called the magnitude, and then we have the angle here that the line makes with the x-axis, and that's typically called the phase angle. So the magnitude, if you remember from the Pythagorean theorem, is just the square root of both of the legs squared. So in this case, 3 squared plus 4 squared. And so the magnitude is 5. Similarly, we can calculate the phase here. And the phase is going to be the arctangent of the y part. So in this case, 4 over the run. So the rise over the run, which is 4/3 here. And if you're intimidated by this arctangent, this is common in MATLAB, Python, pretty much any language under the sun. And you can probably do this on your calculator as well. We can calculate the phase as 0.9 radians or 53.13 degrees. We're going to be working in radians in this video if you're not familiar with that. It's similar to degrees, but it's just a little bit easier to work with sometimes. So let's move on to the Fourier Transform. Now this is mentioned in the book. This isn't used a ton in trading, but it's something that's good to understand. So the Fourier Transform really comes down to this concept of we have something in the time domain, right? So we've got our price. We got price on the y-axis and we got time. So this is in the time domain. But a lot of people don't know that you can represent this in the frequency domain. In the frequency domain, we're going to have frequency on the x-axis instead of time. And on the y-axis, we're going to have power or magnitude, or you can think of this as volume. Usually power is measured in decibels. This shows us the power at each frequency. So you can see at low frequencies, we have really high power. So these are big cycles, and you can see these big cycles here, this big movement. That's high power. And then we've got down here, we've got really low power frequencies, and that's all these little oscillations that usually we want to smooth out with any kind of filter. And so we can go from the time domain to the frequency domain with a Fourier transform. So the Fourier transform is this mathematical expression here, and this looks intimidating at first, but it's really not that bad. So basically what we have here is we've got the transform on the left side, and that's our frequency domain version of the signal. This symbol just means the sum of all values, basically. So from here we're summing from negative infinity to infinity, but in practice you would really just sum over the area that you're interested in. Right here is our time domain function, so that's our price versus time. And this is written as g of t. So this is the price at t. So if you have t is equal to 1, so the first bar, the price at the first bar, price at second bar, and so on. We're doing this sum over t. And then we just have some complex exponential. So we're not going to go into how this exponential expands. You can see that we also have t up here, and then we have a new term, which is f, and that's our frequency. And so if we do the sum of the product of our time domain function, g of t, and the complex exponential, we will get the Fourier transform. And so the Fourier transform basically produces a function of frequency that splits out complex numbers. So you can see here I've taken the Fourier transform, and this is the real component. Remember, it spits out a complex number. So this is the real component. And similarly, we can get an imaginary component. And if you remember from complex numbers, we have a real part and an imaginary part, and we can calculate the magnitude. Now, a lot of times we express the magnitude in decibels, and that is done by 20 times logarithm base 10 of the magnitude. So, if we take the Fourier transform of our time domain price, we end up with our frequency domain, and this is commonly called a PSD, or power spectral density. And again, we can see all of our different powers at different frequencies. If we plot our time, frequency, and power at the same time, it looks pretty weird. But if we zoom in on one side of the graph, we can see our price information. And if we zoom in on the other side of the graph, we can see our power and frequency information. This is a pretty cool way to visualize the Fourier transform. So this is all great, but what does it mean? Like, what's it good for, kind of thing. So let's get into that. And it's useful when we start thinking about filtering. So a filter is something that selectively removes frequencies from a signal. That's what we're doing with a moving average. We're taking our frequency domain and we're removing certain frequency components that we do not want. And so let's look at our power spectral density again. But instead of frequency, now I'm plotting it as cycle period. So this is a number of bars. Now you'll notice that we have our high density, low power signal over here. And this is in the low bar period, and that makes sense, right? Lower bars means higher frequency. Higher bars means lower frequency. So with a filter, what we want to do is basically select some of these frequency components, and we want to filter them out. And we want to let all of the longer cycle periods pass through. And so this is what's called a low pass filter, meaning lower frequencies get to pass through the filter pretty much untouched. And this area is called the pass band. This is something we'll be talking about here in a little bit. So in general, the process of filtering is we take our time domain price series and we apply the Fourier transform to it, and then we filter the frequency domain, removing some of the components that we don't want. And then we're going to do the inverse Fourier transform. The inverse Fourier transform is pretty similar to the Fourier transform, but you'll notice some key differences. The first one is now we've moved our filtered frequency domain. The other thing we've done is we've moved our time series is now over here. The other thing you'll notice is that we're summing over the frequencies this time. And then the last thing is we've dropped the negative sign in the exponential. If we applied this low pass filter where we removed the cycles that are 50 bars or less, this is what it looks like. And that looks pretty good, right? Except that there's one key problem with this. Well, actually two. And I'll let you pause for a second and try to think what that problem is. All right, so the problem is We can only do this if we have all of the price data. We did this filter using all of the price data, so this is not possible when we don't have all the price data. And the other thing is, in practice, if we're calculating a filtered moving average, we're not going to perform the Fourier transform on every bar. So what do? We go to a moving average. Now, a moving average, in this case a simple moving average, we can think of it as a function that multiplies the complex output of our Fourier transform. So we've got our signal in the frequency domain, and then we're going to multiply this filter by that frequency domain. So in this case, we've got bars down here, and then we've got our filter coefficient that we're going to multiply each frequency component by. So in this case, with the simple moving average, our coefficient is 1 over n. And so if we plot our frequency spectrum corresponding to these bars, we're going to multiply this frequency space by 1 over n, and that looks like this. Outside of the filter, we've set all those frequencies to 0. So all these low power, high frequency components, they're going to get set to 0. Similarly, a weighted moving average, older prices have less weight. So over here, we've got less weight all the way down to 0. So this is a 10-period weighted moving average. Now the weight is a little bit more complicated, but all it is it's the bar number, so in this case 1 divided by the sum of all of these. So in this case it's 1 plus 2 plus 3, on and on. That sum is equal to 55. So our weights are going to be each of these numbers here divided by 55, and that's pretty simple. Now the exponential moving average is a little bit more complex. The exponential moving average for 1 is what's called a infinite impulse response filter. And what that means is we've got exponentially decreasing weights. And these weights, they actually never go to 0. So we have to multiply all of the frequencies out to infinity. Now in practice, they get so close to 0 that they are 0. One thing you'll notice is that the EMA does not have a period. A lot of trading software and stuff, they let you put in a period, but technically an EMA has an alpha parameter, and we can calculate an equivalent period from that, and that's usually what people use. But it's helpful to know that exponential moving average is actually defined using alpha. So let's get into some of the special topics in filtering, and that's going to be frequency and phase response, and we'll talk about cycle lag and filter lag. So let's start with the frequency response. So this is something interesting. So if we take our SMA filter, right, and this is right now, this is actually in the time domain, right? So we've got bars down here and we've got the filter coefficient. What if we took the Fourier transform of this? And if we do that, basically what we're doing is we're plugging in our filter in the time domain to the Fourier transform, and we'll get our filter in the frequency domain to see what that looks like. And so that's what this looks like. So for a 10 bar SMA, this is our frequency response. Now we've got our frequency response on the y-axis, and this is in decibels, or power again. And we've got our frequency on the bottom. It shows us what happens to each frequency that passes through our filter. So for an arbitrary price signal, this shows us what's going to happen to each of the frequency components in that signal. So we've got increasing frequency on the x-axis, decreasing period, decreasing number of bars. And you can think of this as a volume slider. So for frequencies up here, the volume is going to be pretty much unchanged, but for frequencies over here, the volume is significantly reduced. So there is an important point on this chart, and that happens to be -3 decibel mark. And this point is important because this point represents half of that frequency's power. So what does that mean? It means anything below this line is reduced in volume, in power, by more than half. Everything above is going to be reduced slightly, you can see, but not very much compared to the rest. Just as we established the power level at which that cutoff happens, we can also establish the frequency at which that happens. And that is called the cutoff or the critical frequency. And that's the frequency at which anything beyond it is reduced by more than half power. And so for the 10 bar SMA, that cutoff happens to be 22 bars. That means when you apply a 10 period SMA, anything less than 22 bars in terms of cycle is going to be completely eliminated. Another important thing here is you might notice this odd shape to the graph. And these right here are called poles. And basically what that means is that there are certain frequency components in this filter that are completely eliminated. The frequencies happen to be 2 bars. So again, I mentioned that 1 over here corresponds to a 2 bar cycle, 2.5 bars, 3 1/3 bars, 5 bars, and 10 bars. So now let's talk about phase and filter lag. Similar to our frequency response, we can look at a phase response. And in this case, I'm choosing to show phase delay because it's a little bit more familiar for people. And so what this shows is the lag at each frequency component, right? Because you can conceive of a filter that might lag different frequencies differently. So a 10 bar frequency might have a different lag than a 20 bar frequency. And so what we're seeing here with this straight constant line is that an SMA has a constant lag, and a 10 period SMA has a 4.5 bar lag. So you might be wondering how to calculate this. Well, you can calculate the phase response first, and this is going to be the angular delay, which is a little bit more complicated to think about, which is why I'm choosing to show the lag in bars. Well, the phase response here I'm denoting as phi. Phi is a function of frequency, and it's equal to the inverse tangent of the imaginary frequency part over the real frequency. And this is going back to our complex numbers thing. Feel free to rewind. I showed how you can calculate the phase angle, and that's exactly what this is. So we're calculating the phase angle of our frequency domain. The phase delay, which is what I'm showing here, well, that is the phase response divided by the frequency. So for each phase that you get at each frequency, you're going to divide it by its corresponding frequency, and that is how you get the lag time at each frequency. Often we're not interested in what's happening to each specific frequency. We just want to know what's the overall lag. So what is the lag of an SMA filter? If we go back to looking at our filter here, well, we can calculate the lag of the filter by thinking of the center of mass of the filter. So if we draw a box here, we want to know what's the center of mass of this box. So it would be somewhere right here, right? And so we want to know this distance. That's where the center of mass is. And so for a 10 bar moving average, that happens to be 4.5 bars. Now you'll notice that that 4.5 bars is the same as what we got in our phase delay on the previous slide. This is something unique to the simple moving average. It's not always that the lag of the filter overall is the same as the phase delay. So for an SMA filter, we can calculate the delay as n minus 1 over 2. That's pretty simple. So instead of showing all of this calculation for all the different filters, I made a little cheat sheet here. And so this cheat sheet has, for each of the moving averages that we use in trading, the simple, the weighted, and the exponential, we've got the cutoff cycle, which I showed, and instead of giving you the frequency, I'm giving you the bars. So remember, the cutoff is the number of bars at which anything less than that is going to get attenuated or filtered out. So for a simple moving average, that's 2 pi n over 2.88. Similarly, for the weighted moving average, I've developed this expression. This is an approximation because the weighted moving average does not have an analytical solution for the cutoff. The exponential moving average does have a closed form solution, and so it's a little bit complicated here, but this is the arc cosine or inverse cosine function, and then it's a function of alpha, you see here. Again, we can calculate the overall lag of the filter. For the simple moving average, I showed you was n minus 1 over 2. For the weighted, it's n minus 1 over 3. And for the EMA, it's 1 over alpha minus 1. Now I've added something on here which is talked about in the book and which I'm going to show a little bit later, but we've also got the SMA equivalent lag. And so this is, the period of the filter, so in this case for the SMA it's n, right? 10 bar moving average, just 10. We want to know what period do we use for the weighted moving average so that it has the same lag as the SMA. And so the way we do that is if we had a 10 period SMA, to get the same lag as a 10 period SMA, we would need to do a 3 times n minus 1 over 2 period weighted moving average. So for a 10 bar SMA, what is that, 14.5 with the EMA? We can just calculate the alpha parameter that would give us the same lag, and that would be 2 divided by n plus 1. So originally I had planned to cover some of the filter analysis and stuff in Python in this video, but this video is getting a little long, so I'm going to save that for its own video. So keep an eye out for the next one. We're going to cover all of this information, but we're going to do it hands-on in Python. And then I'm going to do a little bit of a comparative analysis between different filters. I'm going to show you how to select a filter for your specific trading application. See you next time.